Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper trending on X, published on August 17, 2025, about a week ago. The big hook is a simple add-on called VLAPS that wraps a pre-trained vision language action policy with model-based search, yielding large gains in success on tough, language-driven robot tasks, including increases up to 67 percentage points in some suites. The paper is titled, Improving Pre-trained Vision Language Action Policies with Model-Based Search, and as we will see later, the results are really impressive. In short, the method turns brittle zero-shot behaviors into safer, longer horizon plans by guiding search with the policy's own priors. Building on that, the highlighted tweet says, VLAs can be brittle when followed directly, and VLAPS integrates model-based search to boost performance without extra training. Engagement looks solid with about 150 likes. Alright, we are looking at the overview diagram that spells out how the planning and search pipeline operates. The left side shows an instruction and camera view feeding into a search tree, which grows over macro actions that represent short robot trajectories so the branching stays manageable. The green path marks a simulated task success, while the red node marks a failure discovered during rollouts. On the right, you can see the policy and the world model steering macro action sampling and selection, which then yields the final action sequence to execute. Next, we are looking at a pair of bar charts that summarize success and compute across different fine-tuning steps. The left chart shows task success rate rising sharply with VLAPS, especially at 10,000 and 50,000 steps, where it jumps far above the VLA-only policy. The right chart reports mean runtime, which is higher for VLAPS at low steps, but drops as the base policy improves. Together, these plots show a success boost that justifies extra search and shrinking cost as the policy gets stronger. Now we are looking at a two-panel figure that illustrates the kinds of language instructions and robot views used in the benchmark, which helps explain why macro actions matter. The left panel shows a pick and place with a black bowl and a plate, with a small inset zooming into the target. The right panel shows a pick and drop of salad dressing into a basket, again with an inset confirming the goal. These scenes highlight spatial reasoning and object specificity, so planning over short trajectories becomes especially helpful. Now we are looking at a summary table that reports success rate and mean runtime across the Libro suites and training checkpoints. You can see big jumps for the planning plus search method at early checkpoints, like Libro object going from 6% to 73% at 50,000 steps, which signals strong gains when the base policy is weak. The runtime column shows higher search cost early, then shorter times as the policy improves. Overall, the table quantifies the trade-off, much higher success with manageable compute. We are looking at a hyperparameter table that details how the planning and search procedure is configured, which helps explain the runtime and success trends we just saw. The top block lists search settings, like 10 child expansions per node, a macro action horizon of 4, a maximum depth of 100, and 600 seconds of wall clock time. The lower block then specifies input sizes, with 256 by 256 for the main view and 128 by 128 for the wrist camera. Circling back to the hyperparameters, the big picture is clear. Planning with macro actions, guided by the vision language action policy, turns infeasible search into practical execution and lifts success dramatically, especially when the base policy is weak. A macro action means a short, predefined trajectory, which stabilizes long horizon decisions. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.